Hey everybody, welcome to week 10 of PS 231. So in the previous two lectures, we've talked about how to incorporate time into our book of fables. So 2 weeks ago, we said, okay, well, these simultaneous move games can only take us so far. It seems like the future matters. It seems like some moves precede other moves, or some moves are at the end of time or something like that. So how do we write down fables that respect time that way? And then last week, when we were talking about subgame perfection and the backward induction algorithm, we saw that the way that we analyze these models is to think about collective rationality, equilibrium behavior. We learned how to think about that in a more sequentially rational sort of way, where subgame-perfect equilibrium is something that means that not only is it an equilibrium of the entire game, the entire subgame, but also in each little individual subgame, so that the little fine-grained parts of strategy complement what happens at the big level, and what happens at the big level is amenable to what's happening at the small level. Now, backward induction, or the more general process of looking for subgame-perfect equilibria in finite horizon games, that's all relatively straightforward, easy for me to say I haven't suffered through the problem sets. But this is not too complicated. I wanted to wait for 1 week to show you what this would look like in ultimatum game type behavior, where somebody is setting a level of a variable rather than just making a choice. So I want to talk about that today. I want to talk about how backward induction and subgame perfection apply to continuous action space games. You'll see that it's not that much harder. It's just a matter of being a little bit more flexible with how we think about things. And what's really great is that the substantive punchlines of some of these models are worth a week's delay. So even though we had all sorts of cool substantive stories emerge last week, we'll have more cool substantive stories emerge this week, even though we'll also be learning a somewhat more general method for studying games of this type. I want to highlight the fact that the Ultimatum game is the first real game theoretic procedure for bargaining that we've discussed in this class. So we spent a whole week on bargaining and optimality, and we even did a little bit of a Nash bargaining analysis, a normative analysis, to say, well, what do we think would be the Pareto efficient outcome given some disagreement point? When I introduced the Ultimatum game 2 weeks ago, I mentioned briefly that there's a bargaining flavor to it, but we didn't talk that much about the actual bargaining substance of the Ultimatum game. And this will be a nice opportunity for us to visit with that for some amount of time. So throughout today's lecture, I hope that you have an eye both on the somewhat more general method of analysis, but also on the interesting substantive punchlines that we'll be seeing about how bargaining processes play out, be they abstract bargaining or legislative bargaining or anything like that. So in the A block, I want to show you how we analyze the Ultimatum game. We'll do a couple of different flavors of the Ultimatum game just to help you to see what's going on there. We will pin down a very memorable, unique subgame perfect equilibrium for the Ultimatum game, which is it'll be a moment that's memorable for you, I suspect, and one of those things where you'll get a little bit annoyed with it actually, because the model actually doesn't seem to comport with reality very much, but it's wrong in such a useful way that it'll stick in your head. On the B block, I want to extend that logic a little bit and talk about what the median voter theorem looks like if the two candidates get to set their campaign platforms sequentially rather than simultaneously. There's this influential idea that incumbents have advantages because they get to set the agenda. And that's true in many ways. You would think that it would also be true in this sequential platform setting sort of analysis. And whether or not there's an advantage or a disadvantage of or neither, well, that's going to be something that emerges in our analysis in the B block. And then in the C block, keeping the focus on domestic politics, let's talk about the pivotal politics model and equilibrium behavior there. We'll see that the proposer has a relatively nuanced decision to make, but that once we think that through in this subgame perfect kind of way, we'll be able to tell a really interesting story about what kind of proposals we would expect to see in legislatures, conditional on who's the proposer, who's the median voter, and what's the status quo. So linking these things all together is going to be part of our analysis. What's cool about a class like this is you learn just from seeing the fables, but then you also learn from the analysis, and neither alone is enough. You have to learn the stories and you have to learn how to analyze them. And I hope that this sort of, here's a story and here's how you analyze it, and here's a story and here's how you analyze it. I hope that this is giving you a chance to remember the stories a little bit without having to think too much about their punchlines. But I think some of the punchlines this week are going to be really, really cool. If nothing else, talking about pivotal politics, this is, for those of you that are ever going to go work for a congressperson or something, pivotal politics is still way too simple to get at the heart of real legislative politics. But it gives such a nice framework for thinking about legislative politics that even a non-specialist in the subject like me can try to make some sense about what they read in the newspaper, even though I don't know anything more about Congress than you all do. I probably know less. But being able to think these things through will give you a little more flexibility whenever you read the news and you don't quite know everything that's happening. So I think a lot to look forward to today, even though it sounds like it might be a little bit of a specialist type lecture. I think that you're going to be pleasantly surprised by some of the cool things that emerge today. Let's get started. So I want to start off by talking about the Ultimatum game. We're gonna try to pin down the subgame-perfect equilibria for the Ultimatum game, which you'll remember was the first of the models we wrote down with a continuous action space. It wasn't just like a go left, go right sort of thing. Now it's like a choose some X out of this hoodie logo. So let's just all reacquaint ourselves with the Ultimatum game. So the idea here is that at the beginning of time, player 1 chooses some X that lives between 0 and 1. And no matter what offer is made, country 2 can either accept or reject that offer. If they accept the offer, then the outcome is X happiness points for player 1 and 1 minus X happiness points for player 2. Remember, the happiness depends on what X player 1 chose. And if there's disagreement, let's call that 0-0 for now. Notice that this is a bargaining model. Why is it a bargaining model? Well, for starters, there are competing preferences over the happy outcomes. Player 1 wants X to be high, and player 2 wants X to be low. Notice also that 0-0 is Pareto dominated by any X1 minus X combination so long as X falls between 0 and 1. Any one of those, Pareto dominates the disagreement point of 0-0. Just to show you that, let me just put this into a utility imputation space. So I'll put player 1's utilities on the horizontal axis and player 2's on the vertical axis. Notice that the happiness frontier, it can go as high as 0-1 and go as low as 1-0. And any line that comes in between them, that's an X1 minus X combination. So the Pareto frontier is just a straight line that goes from 0-1 to 1-0. And the disagreement point is exactly at the origin, 0-0. So this is a full-on bargaining problem where we're officially going to try to give an answer about which of the infinite set of Pareto efficient points actually happens. Okay, so let's go back to the game. And how the heck are we going to think about all the subgames? How many subgames does this game have? Well, let's go back to the game. And here's your first pause the video moment. I want you to pause the video and tell me how many subgames there are. Remember, a subgame is a subset of the game, right? It's a subset of the nodes and edges of the game that has a unique root node, doesn't tear apart information sets, and ends only in terminal nodes. So how many of those are there in this game? How many of those are there in this game? Pause the video. How many subgames does this game have? Welcome back. For those two of you that paused the video. So, if you answered infinite, you're right. This game has an infinite number of subgames. What do I mean by that? Well, let me just call some out. There's the subgame that starts from player 2's decision after an offer of x equals 0. includes their accept reject decision, and goes only to terminal nodes. So that's a subgame. There's a subgame that starts with player two's decision after x equals 0 and goes to the end. There's another one where x equals 1 and player 2 has to make that choice. So there's a subgame that starts from player 2's choice after x equals 1. There's a subgame that starts with player 2's choice after x equals 1/2. There's a subgame that starts with player 2's choice after x equals 1/4. There's a subgame that starts with player 2's choice after x equals pi over 1 plus pi. Take your birthday and convert it to digits. So mine is, I don't want to tell you my birthday because then you'll all become identity thieves, but put the month in 2 numbers, put the date in 2 numbers, and put the year in 2 numbers. So now you get 8 numbers. You have an 8-digit number that represents your birthday, okay? That number over 1 plus it, I have to consider that subgame. We just covered all your birthdays. All your birthdays are in this Assassin's Creed logo. All your birthdays belong to us. They're all in there. Think about it. There's an infinite number of subgames, and we have to solve every subgame in order to get to a subgame-perfect equilibrium. The algorithm tells me I have to solve every subgame. There's an uncountably infinite number of them. There is a hopelessly god-awful massive number of subgames in this game. All I wanted to do was look cool and solve the Ultimatum game and teach you something. There's an infinite number of subgames. What am I going to do? How am I going to solve this? Because player 2's strategy, I need to know what player 2 is going to do with every one of those. None of them are linked by information sets, right? So which is to say, at every distinct one of those nodes that player 2, at every one of these distinct nodes that player 2 could be at, we need to know what they're going to do. We need to know what they're going to do. We can't do backwards induction on this because we don't know how the heck to solve all these subgames. None of these decision nodes is solved. None of them are solved. How do we solve them? Well, one at a time? We can't do that one at a time. How are we going to do that? That's tough, right? That's tricky. Well, let's think about it. What we need is a device. We need a device that reads in an offer. X equals 1/2, X equals 3/4, X equals your birthday over 1 plus your birthday. Right? We need that. It reads in something between 0 and 1, and it spits out accept or reject. Player 2's options. So I need to know how to turn any one of these offers, because there's an infinite number. I can't handle them all by myself. I need to come up with a device that does that for me, because if I try to do them all, I'll be dead soon. If I did one a day for the rest of my life, I still wouldn't be anywhere close. Uncountably infinite is very large. So how am I going to do that? I need to find a way. I need a tool that reads in something and spits out something else. What's that? What'd you say? Oh, stop whispering to yourself. What'd you say? Yes, you. What'd you say? Oh, a function. That's right. You just got a participation point. Congratulations. And you're like, is he talking about me? Yes, I'm talking about you in particular. Congratulations. I got to keep myself entertained. So player 2's strategy in this game is a function that reads in 0, 1, closed interval. It reads in all the possible offers. It reads in every possible X. And it spits out accept or reject. Pretty cool, right? Player 2's strategy is a function. That's going to be a recurring theme. So now it's not just a matter of, when the decision nodes were finite, it's just like go that way, go that way. Now it's like, how do you choose a rule to send offers into accept or reject? Now we need to think through what that function looks like. Okay? So let's just zoom in. Let's just think about one possible instantiation of the game. So suppose that x equals 1/2. Okay. Well, if x equals 1/2, then that means the current offer on the table gives player 1 a half a happiness point and player 2 a half a happiness point. And rejecting that offer would give player 2 0 happiness points. So sequential rationality tells me that if x equals 1/2, then the only rational output of that function is accept. Now suppose x equals 3/4. So if x equals 3/4, then player 1, if that offer is accepted, gets 3/4 of a happiness point, and player 2 gets 1/4 of a happiness point. 1/4 is still strictly bigger than 0, so player 2 would accept that offer. What about 7/8? Well, that would leave player 2 1/8 of happiness point, which is still strictly greater than the 0 that they get for rejecting. So they would accept, if x equals 7/8, they would accept. 15/16, they would accept, they like 1/16. 31/32, they would accept, they like 1/32 more than 0, strictly so. 63/64, 127 128ths, 255 256ths, and so on. They would accept every one of these offers because every one of them gives them strictly more than the 0 that they get for disagreement. I could offer them a Google over a Google +1, and they would be strictly happier. It sounds like a cups of coffee problem just waiting to happen, but let's just go with it. So the idea here is that if x is strictly less than 1, acceptance must happen. If x equals 0, accept. 1/2, accept. 3/4, accept. 7/8, accept. 15/16, accept. Every offer where x is strictly less than 1 has to go to accept. There's no ambiguity. Okay? So long as player 1 offers a little bit of this to player 2 will accept it because it's strictly better. So if I'm filling in player 2's strategy and I'm doing it piecewise, you'll see why I'm going to do this in a moment. Then I'll put a sub 2 of x. A sub 2 of x. It reads in an x and it spits out an action. A sub 2 of x equals accept if x is strictly less than 1. Okay? That's pretty straightforward. What if x is equal to 1? Now things get a little bit tricky. Well, if x equals 1, then that means that the 1 minus x that party 2 gets is 0. They get 0. They get 0 happiness points. So they get 0 happiness points if they would accept the offer, and they get 0 happiness points if they reject it. So either is possible. Those are both the best response, right? We've said throughout that if somebody is indifferent, then either one is possible. Therefore, my strategy function has to be accept or reject. It has to spit out either if x equals 1. Either is acceptable. And we'll think about both of those contingencies separately. Okay? Regardless, let's consider player 2's decision solved. That's solved because for every one of the infinite parts of the Assassin's Creed hoodie, for every one of those infinite things, our function allowed us to do that. The fact that a strategy was a function made this very simple and straightforward. What seemed like a crisis actually wasn't that big of a deal. We just had to be flexible. We had to consider the world where player 2 rejects when indifferent, and the world where they accept when they're indifferent. Okay? Let's consider those two in turn. So suppose for now, the player 2's strategy is to accept anything strictly less than 1, but to reject x equals 1. They reject that. Let's suppose that they rejected that. Okay? Now let's move up a node and think about player 1. Player 1 now has looked down the tree. They've looked down the infinite tree. And they've said, okay, I know that as of right now, player 2 will accept any offer that I make where x is strictly less than 1. But they'll reject if x equals 1. Right now, that's our hypothesis right now. We're saying, suppose for now that player 2 is a rejecter when indifferent. They reject when they're indifferent. Okay? Let's think about what's best for player 1. So if they offer x equals 0, that's accepted and they get 0 happiness points. If they offer x equals a quarter, they get a quarter because it gets accepted. If they offer x equals a half, they get a half because it gets accepted. If they offer x equals 3/4, it gets accepted and they get 3/4. If they offer 7/8, it gets accepted and they get 7/8. If they offer 15/16, it gets accepted and they get 15/16. If they offer a Google over a Google plus 1, it gets accepted and they get to keep a Google over a Google plus 1, which is very close to 1, but is strictly less than it. Okay? So here's a question for you. What is the largest number strictly less than 1? Because that's the number they want. 0 isn't an equilibrium offer because it gets beaten by a half. A half isn't an equilibrium offer because it gets beaten by 3/4. 3/4 is an equilibrium offer because it gets beaten by 7/8. 7/8 isn't an equilibrium offer because it gets beaten by 15/16. 15/16 is not an equilibrium offer because it gets beaten by 31/32. 31/32 is not an equilibrium offer because it gets beaten by 63/64. 63/64 is not an equilibrium offer because it gets beaten by 127/128. 127/128 is not an equilibrium offer because it gets beaten by 255/256. 255/256 is not an equilibrium offer because it gets beaten by 511/512. What's the biggest number strictly less than 1? There isn't one. There is no best offer to make. And you don't want to go all the way to 1 because that's going to get rejected and you get 0. Player 1 is in a pickle. Player 1, the only way there could be an equilibrium of this type is that player 1 managed to find the largest number strictly less than 1, which doesn't exist. There is no equilibrium of this type. This is because of the infinite part. If we had divided it into, let's say I had $1 and I divided it into pennies. I could only divide it into pennies. I had 100 pennies. I can't melt down the pennies any further. If there were only 101 different things I could offer you, 0 pennies, 1 penny, I keep 0, I keep 1, I keep 2, I keep 3, ... I keep 100. There's 101 of those. Okay. If that had been the case, and you were rejecting when indifferent, let's say that you rejected when indifferent. So if I offered to keep all 100 pennies and thus you got 0, you could reject that. That's where we are right now. But because it's finite, my next move down, I could say, okay, I'll keep 99 pennies and you keep 1. And you would accept that because the 1 penny is strictly better than the 0 that you were getting if you reject. So if it were discrete, I would have an easy time of it. If this was a discrete set of options, if I could count them all, or if I could assign every one of them a counting number, this would be very easy. But it's the fact that I can't find a strictly largest number strictly less than 1. That's the trouble. So you can imagine a continuous thing like this as an approximation of a discrete thing like I just described as the units get very tiny. Now, for regular people like us, it isn't very common for us to be able to talk about fractions of a penny. But in very large deals, fractions of a penny might matter quite a bit. And so you can think about this as that's a very small unit on a very large deal, right? So you can think about this ultimatum game as we've drawn it with the continuous hoodie. That's just an approximation of what would happen if the pennies got very small. I mean, think about it. So we all have pennies. Think about the ratio of the smallest unit of currency that a regular person could have versus how much a Diet Coke costs in that place. Right? So here a Diet Coke costs 100, let's say a Diet Coke's $1. That costs 100 units of the smallest thing that a regular person can get, 100 pennies. Suppose that inflation went up. Suppose that instead of $1, a Diet Coke cost $1,000. And everything else along with it. Just suppose the price of everything went up by 1,000, a factor of 1,000. Do you think we'd still be carrying around pennies? We wouldn't still be carrying around pennies. No. Just look at the currencies of some places that have suffered from hyperinflation, and they'll tell you that they don't carry around pennies. So this continuous thing is just our way of saying, oh, I don't have to worry about this. I just want to say, just imagine that the units were small enough that they could be viewed as if they were continuous. And what we just learned is that created a real wrinkle. That just created a very real wrinkle. So there is no equilibrium where player 2 rejects when indifferent. Because in order for there to be such an equilibrium, it would have to be the case that player 1 found the optimal offer that was still acceptable. And there wouldn't be one. Because for anything that they thought that they found, we could get a little bit better for them. No equilibrium. No equilibrium. That's why I wanted to wait a week. I wanted to wait a week. This is worth talking about for a second, right? So suppose instead that player 2 accepted when indifferent. We said that's a possibility. That's just as equilibrium-y as the other thing, right? Suppose instead that country 2 accepted when indifferent. So they accept all offers. They accept any x strictly less than 1. And now they also accept x equals 1. Well, let's go up a step. Let's think about player 1 now. What's the best offer that player 1 could make? Now it's easy. They just offer x equals 1, which they know is going to get accepted. Now they don't have to worry about finding the largest number strictly less than 1 because they can just offer x equals 1 and they're good. So that's the unique subgame-perfect equilibrium of the Ultimatum game. The unique subgame-perfect equilibrium of the Ultimatum game is player 1 offers x equals 1, which is accepted. Player 2 accepts all offers. That's it. That's the equilibrium. So I want to highlight an important concept, and in order to do that, I want to actually talk about the Nash equilibria of this game. So what are the Nash equilibria of this game? Not the subgame-perfect. What are all the Nash equilibria of this game? Okay. So I claim that the following is a Nash equilibrium. X equals 1/2. So player 1 sets x equals to 1/2, and player 2 accepts all x's less than or equal to 1/2 and rejects all strictly greater. So that's my profile. And in equilibrium, that's accepted then, right? Well, does any player have an incentive to deviate? Well, if player 1 deviated something strictly less than 1/2, it would be accepted and they would get that, which would be strictly less than the 1/2 that they're getting now. So that's not profitable. And if they deviate to something strictly greater than 1/2, it would be rejected and they would get 0. So they don't want to deviate that way either. Player 1 doesn't want to deviate. Player 1 is happy at the profile that I just described. Player 2, well, if they deviated to where they'd be rejecting at this position, they would get 0 and be strictly worse off. So player 2 doesn't want to deviate. So the profile that I mentioned, x equals 1/2, and player 2 accepts all offers less than or equal to 1/2 and rejects all offers strictly greater. That's a Nash equilibrium. There's nothing special about 1/2. I could have said 1/3 or 1/4 or 3/4 or your birthday over 1 plus your birthday or a Google over a Google plus 1. I could have chosen any number and used the same story. So suppose that the offer was your birthday over your birthday plus 1. And that player 2 was accepting that and lower and rejecting anything strictly higher. Still a Nash equilibrium. This game has an infinite number of Nash equilibria. An infinite number of Nash equilibria in this game. Infinite. Uncountably infinite. This game has as many Nash equilibria as there are possibilities on the hoodie. Nash style. But once we actually respected the time structure of the game, now it has one and only one equilibrium. which happens to be the one that favors player 1 all the way. So we went from infinite number of equilibria, some favor player 1, some favor player 2, some are strictly in the middle, to the one where player 1 got everything. We call that first mover advantage. That's what it looks like. Without time, this game had an infinite number of equilibria, and we couldn't tell you who was the winner and who was the loser, or if it was perfectly egalitarian. Couldn't tell you. Once we added the time structure and respected it by analyzing via backward induction, we came up with a unique equilibrium which favored player 1 all the way. They're the first mover, they have the advantage. That's pretty cool, right? That's what we mean when we say that. There would have been many equilibria if we didn't have the time structure, but the time structure conferred benefits to player 1. Isn't that cool? Now, it's not cool in the sense that now we have this very nasty outcome, but that isn't just because of the first mover advantage. First mover advantage isn't all the way decisive in a game like this, right? What do I mean by that? Well, notice that the disagreement point of this model was 0, 0. What if we tweaked it? Let's say instead that let's keep player 1's disagreement point at 0, but let's say the player 2, let's say they get a half. Let's say that if an offer is rejected, player 2 gets 1/2. They don't mind disagreement as much. So we tweaked the model. Now what? Well, we work backwards. So we have to come up with the appropriate strategy function for player 2 now. It's different than it was before. Notice that if x is strictly greater than 1/2, then 1 minus x is worse for player 2 than the 1/2 is. So they would like, for sure, there's no ambiguity, they would like to reject all offers where x is strictly greater than 1/2. Similarly, they would like to accept all offers where x is strictly less than 1/2. Those are all worlds where they get something strictly better than the 1/2. However, if x is exactly equal to 1/2, now player 2 is indifferent, and they could either accept or reject. Okay, so the only sequentially rational thing, there are two actually, they always accept if x is less than 1/2, they always reject if x is more than 1/2, and if x equals 1/2, they could either be the accepting indifferent person or the rejecting indifferent person. Consider those nodes solved. Now we go up a step. Let's think about player 1's utility for all of the respective x's. Well, if x is less than 1/2, then they get to keep x. And if x is strictly greater than 1/2, then they get 0 because it gets rejected. And just the same way as before, if player 2 is rejecting when indifferent, now player 1 would have to find the largest x strictly less than 1/2. No such number exists. So throughout, we're going to have player 2 needs to be accepting when indifferent. That's a result. Okay, before I go too much further, sometimes you hear people say, oh, and you have to assume that player 2 accepts when indifferent. No, you don't. We just considered very thoroughly the possibility that they didn't accept when indifferent. We considered incredibly thoroughly the situation where they reject when indifferent. We analyzed it. We said, oh my goodness, we would have to solve deep problems in the real numbers. It is not an assumption that player 2 accepts when indifferent. It is a result. I'm looking at the microphone. It's a result. The only way you can get an equilibrium in a game like this is if player 2 accepts when indifferent. It's a result. The first time that one of my teachers said that to me, I was just like, I had to go take a walk. I was so floored by that. I had to go take a walk around campus. So, player 2 accepts at x equals 1/2. This means that player 1 then should offer x equals 1/2, which is accepted. So notice now that we have this perfectly egalitarian outcome, x equals 1/2, 1 minus x equals 1/2. We have completely nullified the first mover advantage of player 1. How? We gave player 2 bargaining power. So there's actually two sources of power in bargaining. One is get to be the agenda setter. Get to move first. Be the person that sets the terms of happiness. The other option is just don't mind disagreement all that much. So in international relations, you see models like this get used a lot. That just means be really strong or have low war costs or something like that. Have a good outside option. Have a strong friend. Legislative politics is a lot harder, right? There are fewer outside options. It turns out that you're not allowed to go ask one of your fellow legislators if they want to form an alliance against the other one and agree to beat them up anytime that they attack. So bargaining is not just about the protocol, and it's not just about bargaining power. It's about how the protocol, who moves first and when, and are there counteroffers allowed, all the different institutional and procedural impositions that we could make. That's one set of the way that we get to outcomes. Bargaining power through good disagreement points is another. Just to show you this, let me put this into utility imputation space. Let's consider the first world where the disagreement point was 0, 0. First mover advantage essentially means that player 1 gets to take the disagreement point and take a horizontal line and go directly to the right. Find where that horizontal line hits the frontier and call that the offer. That's where they're going to wind up. So when the disagreement point was 0, 0, the horizontal line, the first mover advantage line, took us all the way over to 1, 0. When the disagreement point was 1/2, that horizontal line took us over to 1/2, 1/2. The better the player 2's disagreement point is, the higher the horizontal line has to be, the better for player 2 the final utility imputation is. Player 1's bargaining power doesn't matter in this model at all. We're essentially saying player 1 gets to draw horizontal lines, but which horizontal line they get to draw depends on how strong player 2 is. That's pretty cool. That's bargaining. Bargaining isn't just about institutional power, nor is it just about bargaining power. It's about both. That's pretty cool. Consider the set of all points that are Pareto efficient and Pareto dominate the disagreement point. We'll call that the bargaining range. If the disagreement point is 0, 0, then the entire frontier is the bargaining range. But if the disagreement point lives inside, then not all of the Pareto efficient outcomes of the are better than the disagreement point. And what we're saying is, what first mover advantage is it says that whoever is the first mover gets to find the part of the bargaining range that is best for them. So bargaining power determines the bargaining range, and then institutional power says you get to choose whichever of the bargaining range outcomes are best for you. Now, if I have a lot of bargaining power, then all of the bargaining range might be bad for you, but at the very least, you can find the best among those awful alternatives. Okay? So if I'm making an offer to a really strong country that if they reject me and we go to war, I can still make an offer that's the best possible situation that doesn't get me hit. It might be bad, but at least I have first mover advantage. So that's first mover advantage in the context of this ultimatum game, and also how to study this ultimatum game, and also why infinite things are way harder sometimes than finite things, and sometimes it's vice versa. There's a lot going on in this Assassin's Creed logo. There's just a lot of intrigue here, right? Now, on your problem set, we'll talk about what happens if you repeat this process, and we'll see how the institutional structure of alternating offers plays out. But if nothing else, I think this is pretty cool to begin with, don't you? And you're like, no, I'm not so sure. Tastes differ. All right, so it's with this sort of logic in mind that I want to talk about how elites might be thinking about how to use first mover advantage while they have to respond to the masses, right? So let's talk about sequential campaigns in the B block. So suppose that two candidates were running for office and that one of them got to set their agenda first. Maybe their big convention happened first in the year. Or maybe they're the incumbent and they've had a chance to control the agenda for some amount of time. Now, we were just discussing the importance of first mover advantage that we saw in the Ultimatum game, and it's interesting to wonder if incumbents have similar procedural advantages that come from being able to set their platform first, right? So in order to answer that question, let's think about a simple sequential campaign model. And let's just make this look very Ultimatum game. So at the beginning of time, candidate A, the incumbent or the early campaign, the person that comes out early in a primary, at the beginning of time, that candidate can set some agenda, call it X, that lives between minus infinity and infinity. We'll call this policy space, this the real line. So they choose some platform in the real line. Very positive numbers would be very leaning right ideas, and very negative numbers would be very leaning left ideas. So that, where the lefts are, the left is, and where the right are, the right. I don't want to say liberal and conservative because even that just gets people irritated. I don't want to talk about that. But imagine there's a policy dimension. So candidate A, they choose some platform on that dimension. Candidate B observes that. Let's say candidate B observes the platform and can react. So candidate B then chooses some other platform, Y. Now, there's an infinite number of subgames again, right? So candidate B has to be able to respond to every possible X. And regardless, after candidate B has set their platform, a median voter can vote. And essentially, we're going to say the median voter will choose whichever candidate has the closer platform to their ideal point. So if they vote for A, then they get the negative absolute value of their ideal point minus X. And if they vote for B, then they get the negative absolute value of their ideal point minus Y. As for the candidates, let's just say that they prefer winning to losing, so they get 0 for losing, 1 for winning, and B if X equals Y and they tie. What are the equilibrium platforms going to be? That's the interesting question here. Is player A going to be able to choose a platform that benefits them? Or are they going to be able to win this election more easily because they were able to set the platform? Well, let's see. So, technically speaking, we need to analyze the median voter's decision first. Let's just say that if candidate A's proposal is strictly closer, then they vote A. If it's strictly closer, if B's is strictly closer, they vote B. And if indifferent, they just toss a coin. So there's not a whole lot of intrigue. The voters are robots here. They just look at the two platforms, and if one is closer than the other, they choose the closer one. Otherwise, they toss a coin. Okay, so let's go up a step. Let's think about candidate B's decision. All right, now they have already observed an X by this point. They are reading in an X. They need a function that reads in X's. It reads in real numbers. They need to be able to consider every possible platform for candidate A. We need a function that reads in X's and spits out Y's, which is to say it reads in real numbers, all the possible X's, and it spits out real numbers, all the possible Y's. Okay. Notice that if X is not exactly equal to the median voter's ideal point, let's just visualize this. If X is, without loss of generality, let's say X is to the right of the median voter's ideal point. So imagine the median voter is at some point in the policy space. And suppose that candidate B is thinking about how to respond to candidate A's proposal, their platform, which is more conservative than the median voter's preferences. Okay. What is the best response to that? Which can you choose? Well, notice that any option that is strictly to the left of X and strictly to the right of 2x hat m minus x that lives in this range. So they can choose any y that lives in this open interval. It doesn't have endpoints because otherwise they'd allow indifferences and they would only win half the elections. They want to win the whole election. So they need to be closer. They need to be strictly closer to x hat m than x is. But for any x that isn't there, for any x that isn't right on x hat m, there's a range of possibilities. So if I want to write out player 2's best response to x, I want to write out their choices for x. It reads in an x and it spits out a set of best available platforms. So if x is strictly greater than x hat m, then you could choose anywhere that lives strictly between 2x hat m minus x and win. Not looking like a first mover advantage this time, is it? Similarly, if x was strictly less than x hat m, then you would be able to choose anything between x and 2x hat m minus x. You'd have the same range, just with which label is which flipped. So no matter what, so long as x doesn't equals x hat m, so long as the platform isn't exactly equal to the median voter, player 2 can win the election. Player B can win the election if they want to. They can win the election for sure. So these nodes are all solved. We know what they'll do for any x. If it's strictly greater, they'll choose one of this range. If it's strictly less, they'll choose one of this range. If x equals exactly x hat m, well, then the only best thing to do is to set y equals x hat m. Why? Well, if you go to the right of that, you lose. If you go to the left of that, you lose. If you set y equals x hat m, at least you tie. Okay? So consider all of the nodes for candidate B solved. Again, we just need to think through this all on a functional level. We need to be able to read in every possible platform for candidate A and spit out what is best for candidate B. That's our job here. So now let's think this through for candidate A. So if they choose any x greater than x hat m, the median voter's ideal point, if they choose any platform to the right of the median voter's ideal point, then candidate B will choose one of those things that win. And candidate A will get 0 happiness points. Or, if they choose a platform left of x hat m, if they choose a platform left of the median voter, then just the same way, candidate B will be able to find some option closer to the median voter and win, and candidate A will get 0 happiness points again. However, if they set x exactly equal to x hat m, then candidate B will do the same thing, and they will tie, and they will both get a half a happiness point, which is better for player A than the other alternatives. The unique subgame perfect equilibrium of this game is candidate A sets their platform at the median voter. Candidate B sets their platform at the median voter, and the median voter tosses a coin. That's pretty cool, right? Now, how would you amend this to make it a little bit more realistic? I'm not sure if you noticed, but be it sequential or simultaneous, most candidates are not making a mad dash for the middle. I don't know if you watch the news. Candidates don't have a habit of saying, oh, let's get that median voter real happy. Why is that? Well, there's lots of reasons. You could take whole classes, you could do whole PhDs in that. That's a hard question, right? One easy way to amend this would be to say, well, what happens if the two candidates actually have policy preferences and aren't just trying to get elected? What happens if they actually care about which policies emerge as well? That's what we're going to answer on your problem set. That's an interesting wrinkle, but there's all sorts of wrinkles. But this is a Mr. Potato Head doll. The median voter theorem is a Mr. Potato Head doll. It's not supposed to be finished as it is. It's supposed to have holes in it so that you could put hats and noses and glasses on it. It's beautiful like that. So I just wanted to, because I wanted to put a problem like this on your problem set, I thought it'd be really fun to talk this through a little bit. So that's all that's happening. Just think through this functionally. All right? And you'll be just fine. Actually, You know who has the advantage in this game? Who has the advantage in this game? Who has the advantage in this game as we've just written it down? The median voter does. The median voter ends up getting exactly what they want. The median voter has a last mover advantage. Right? Essentially, what just happened was we went from a world where I make an ultimatum offer to you and you can take it or leave it. And because of that and some weird things about the real numbers, I get to offer to keep everything, you accept it, and that's an equilibrium, and I have first mover advantage. And that took an infinite number of Nash equilibria and turned it into a unique equilibrium. Right? Here, the game, if we didn't respect time, this game already had a unique Nash equilibrium where they both set their profile, they both set their platform at the median. So this isn't like an advantage thing. But substantively, all of the power in this model is in the median voter's hands. So just because somebody gets to move first, and just because it looks like an Assassin's Creed hoodie, that doesn't mean they have a first mover advantage. First mover advantage has nothing to do with the pictures that we draw. First mover advantage has to do with the stories that we tell. First mover advantage has to do with how the disagreement point aligns with the offers, aligns with outside options. It's not just a matter of I see a little curvy thing and that means first mover advantage is happening. No, we think about these things. So this is a weird way to turn the whole idea on its head, which is what I'm trying to do with you here. But if nothing else, I hope that this helps you to see campaigns a little bit differently, because it suggests that although response might matter, although observation and response might matter, there's a voting day. You know? There's a voting day. Now, a lot of things happen in the middle. There's all sorts of opportunities for screwing up and fundraising and activist donors, making your war chest bigger so that you can spend more money, but you have to make policy concessions in order to keep the activists happy. There's all these different things happening. Right? But you could just add those to this and you'd be able to tell a really cool story. But you begin from a very interesting, stark starting point. How do you move the needle away from the median voter? Because I'm not sure if you noticed, but policy preferences do not always favor the median voter. Campaign platforms do not always favor the median voter. Why is that? This model seems very compelling, doesn't it? So what would you add? How would you modify this model? I'm going to show you one on the problem set, but there's a million you could do. Get creative. If you care about politics, you'll have way more answers at your disposal than I will. I don't know the first thing about this. But it's interesting, isn't it? I would have thought the time structure would have mattered going into this, but then you think about it for a second, where by think about it, I mean engage in the sort of behavior analysis that we're talking about today, and suddenly it's very clearly a situation where the median ideal point still wins out. So I want to keep the focus on policy spaces by talking about the pivotal politics model that we introduced a couple of weeks ago. So let's head to the C block. So I want to revisit the idea of the pivotal politics model, which I described to you before as just an ultimatum game, which it is. And the basic idea is that you'll remember that in the pivotal politics model, a proposer, some legislator, has a chance to make a policy proposal in some policy space, and then a median voter compares that proposal against the status quo. So maybe like the chamber median, you get mentions, you see this mentioned sometimes. So whoever is the House median or the Senate median, right? Or even in the context of courts, you can see the Supreme Court median. Whoever is the decisive voter. Notice also that it doesn't have to be the strict median. So although the days of the filibuster seem to be coming near to an end, it could be that you care about the 60th voter. Or if you need a supermajority, you might care about the 2/3 voter or the 3/4 voter. Whoever is the decisive voter is the person with the power. And in regular majority rule, that's the median voter. But sometimes you need a stronger rule than that. Regardless, the idea here is that some pivotal voter, who we'll continue to call the median, can then either accept the proposal or say, no, I'd rather have the status quo. Okay? And the question is, what does that look like once we've thought about it from a subgame-perfect sort of standpoint? So let me just start by drawing pivotal politics. So I'm going to draw without loss of generality. I'm going to say, suppose that P, the proposer, suppose their ideal point is to the right of M, the median's ideal point, which in turn is to the right of Q, the status quo. And eventually we'll think about how this goes as we move the median ideal point throughout the space. But this will give us a good starting point. So here's our space. And remember that this can be animated as an ultimatum game, right? So at the beginning of time, the proposer, P, they chose some proposal, call it little p in X, which is the policy space. So they choose some little p, all right? Which they could choose any number off the real line. They could choose any number off the real line. So it's just choose some part of a platform space, choose some part of a policy space, okay? And then the median voter observes that, and they can either accept or reject it. Well, now we can go by backwards induction. Again, there's an infinite number of proposals that the median voter has to be ready for, so we need a function. We need a function that reads in proposals and spits out accept or reject. So the proposer, in a perfect world, right, they would just propose their ideal thing, but that might lie outside of the win set. That might be outside of where the median voter would like to be. Okay? So let's think about what the median voters accept-reject decisions look like. Well, any proposal to the left of Q, that's even worse. That's further from the median ideal point than Q was, by definition. So that's no good. Those are all going to get rejected. So anything strictly less than Q will get rejected. If the proposal is exactly equal to Q, then that leads to indifference, and we're going to have to think about that. That could be accepted or rejected. Let's just put a pin in that for now. If the proposal is strictly greater than Q, but strictly less than M, or less than or equal to M, so we still haven't made it to the other side. So that's all going to get accepted for sure, because that's closer to M. And even if we go past M a little bit, we can go a little bit past M. How far can we go? Well, so long as we're still to the left of 2M minus Q, it's closer. This is still closer. These parts are all still closer to the median ideal point than Q is, even though they're on the other side. The proposer's preferred side, I should add. Okay? So anything to the left of 2M minus Q, they still accept. At 2M minus Q, they are exactly indifferent between Q and 2M minus Q. So again, we got to put a pin in that. And anything strictly to the right of 2M minus Q is too far to the right for the median ideal point, from the median voter's perspective. And that all gets rejected. So if we just draw this, it's too far to the left gets rejected. There's like this little indifference flashpoint, then there's a sweet spot, there's like a Goldilocks solution, not too far left, not too far right, just right. And then there's another little indifference point, 2M minus Q, and then anything to the right that gets rejected as well. Now, if 2M minus Q is greater than P, then the proposer can just choose P, and that's it, right? If P lived in the win set, they would just say, okay, actually my ideal point is what I propose. The median voter would be like, well, I'm happy for you, I'm also happy for me, I accept. Right? So we're going to have to think about that continually. But the first step is just to get this first. We just got to see this. We got to see what the median voter's appropriate strategy will be under sequential rationality. So we consider all of the median voters' decision nodes solved. Now we know what they'll do as a function of the proposal. If it's too far to the left, they'll reject it. If it's too far to the right, they'll reject it. If it's close enough to their ideal point, they'll accept it. And we still don't quite know what they'll do when they're indifferent. So if X equals Q, they could accept or reject. And if X equals 2M minus Q, if you propose that little mirror image point, 2M minus Q, then that we don't know yet. That could be accepted or rejected. Do you have a guess? You should have a guess in your mind. So we consider all those nodes solved and we move up a step. So what should the proposer propose? As we were just discussing, if their ideal point lives in the win set, if they could choose P, and that if P was strictly less than 2m minus Q, then they would just choose their ideal point, have it accepted, and that would be great. So in order to keep this interesting, let's suppose otherwise. Let's say instead that they could choose that P was to the right of 2m minus Q. So now they couldn't propose P. If they proposed their ideal point, it would get rejected, and they could do better. There's something better they could do. So the question then becomes, what's the best acceptable proposal? Right? Because there's a lot of proposals that beat Q. Q is really far away from the proposer's ideal point. So the question is, what is the best acceptable proposal? Let's consider first the world where the median voter rejects if x equals 2m minus q. Which is to say, they reject when indifferent on the conservative side. So if that's the case, then now the proposer is thinking to themselves, well, I gotta find the proposal furthest to the right that's also strictly less than 2m minus q. For the same reasons we've been discussing up to this point, there is no such proposal. So there's no equilibrium where player 2, where the median voter is rejecting when indifferent at 2m minus q. However, suppose instead that the median voter accepted x equals 2m minus q. They're indifferent. They're indifferent between q and 2m minus q. Let's suppose that they accepted when indifferent there. Well, if that's the case, then now the proposer is saying, I can offer exactly 2m minus q and get it accepted. Anything to the right gets rejected. Anything to the left that's still in the win set gets accepted but is worse for me. The best thing that I could do is offer 2m minus q and get it accepted. And indeed, the unique subgame-perfect equilibrium of the pivotal politics model in this form is when if P is far to the right, far enough out that it's far away from 2m minus q, then the unique subgame-perfect equilibrium of pivotal politics is for the proposer to offer 2m minus q, and for the median voter to reject all things strictly less than q, accept or reject q, accept all things strictly between q and 2m minus q, accept 2m minus q, and reject everything strictly greater than 2m minus q. So what the median voter has to do here is pretty complicated, but in response to it, all that the proposer has to do is say 2m minus q it is, and that's our new status quo. I just improved the status quo. The median voter here is precisely indifferent over where she was at the status quo. So there's a first mover advantage in the sense that the proposer gets to find the best thing that's acceptable, right? But the ultimatum game type logic ensures that they have to still make an acceptable offer, right? If the median voter's ideal point is very close to Q, then the median voter essentially has a lot of bargaining power, and there's only so much change that the proposer could make. However, if the status quo is very far from the median voter's ideal point, then the median voter has very little power. And consequently, if that gap is big, then the proposer is going to be able to get their ideal point. So it's just the ultimatum game with this seemingly decisive median voter, but the proposer is getting what they want if there isn't enough bargaining power on the median voter side. And who determines that? The way that the median voter interfaces with the status quo. If the world is out of balance, if the policies in place are out of balance with the current median voter, with the current accumulated preferences of society, then it's very easy for the proposer to get a good proposal for them. But that might be very extreme. They might be able to get something just as extreme. So if let's say Q was very far to the left, the median voter was in the exact middle, and the proposer was very far to the right. The proposer is going to be able to create an equally polarizing outcome. they're going to be able to come up with an outcome that is just as disharmonious with the accumulated preferences of society as the status quo was. They have first mover advantages. The disagreement point, the origins of bargaining power for the median voter are actually, if the median voter has bargaining power, that means that the status quo isn't that far from society's accumulated preferences. That's pretty cool, right? So if we think about M moving from left to right, right? So let's say that M was left of the status quo. Well, now the proposer, they're not gonna make a proposal. They'll just keep the status quo. The status quo is as well as they can do. If M was exactly equal to the status quo, same thing. M strictly greater, that's what we were discussing. But as we move it further and further and further, then things are getting better and better and better for the proposer. What? And once we get to the right, if the median voter is to the right of the proposer is just going to keep things as they are again. They're just going to get their ideal point. So in other words, the expected outcome depends on how the Q's, the M's, and the P's relate. And so do the associated utilities. No. So this model, this very simple model, has a lot of bite. Just by moving M across the space, or changing the order of the Q's and the M's and the P's, the status quo, the median voter, and the proposer, we're able to explain a wide variety of potential outcomes. It might be the proposer gets exactly what they want. It might be the median voter gets exactly what they want. It might be that the status quo is upheld. It might be that a big change is made. It might be that no change is made. It might be that a small change is made. All of these differences in the endogenous equilibrium behavior are about simple combinations about what's going on with the exogenous policy preferences. Chewy says hi. No, quiet. Now again, this isn't quite how things seem to play out, right? So how would you add parties to this? Political parties. How would you add congressional committees to this? How would you add the president to this with veto power? Right? So this simple model and simple subgame perfection here, that's just the beginning of the journey. This is just another potato head doll. The equilibrium behavior can sometimes be a call to action where you're like, okay, the equilibrium behavior in this very plausible model seems very perverse with respect to the real world. I got to figure out what kind of hat to put on this potato head doll. Right? Or sometimes it seems to get things perfectly. I think that the pivotal politics model, which is really just the ultimatum game, it's a nice way to think about the beginnings of political processes. You know, there's a policy dimension in question, and some fresh-faced legislator just got to Washington, and they want to improve the status quo on one dimension meaningful to them. Right? And it might be something super wonky. It might be something about corn subsidies. Here we are in central Illinois. It might be something about something super wonky that doesn't get a whole lot of partisan interest, and the media aren't involved, and the president doesn't care, or whatever, right? If that's the case, then maybe the pivotal politics model is a good way to proceed. All they got to do is find the person that matters on this particular topic, the median voter, the filibuster pivot, the single most important person on about this, whatever it is. And they got to figure out how to find the 2M minus Q thing, right? They got to think through that process. However, some other kinds of issues that emerge in Washington are probably a little bit less straightforward. However, the policy space will always be there, won't it? I mean, I think the policy space part is pretty compelling. The fact that there's a decisive voter is pretty compelling. The question is, how do intermediate parts of the journey, bargaining over the wording of the bill, getting through committee, getting the donors on board, getting the party on board, talking to the president, all of that sausage making might come in between seeing the policy space and making a proposal in really interesting ways. But once you see the problem this way, then the way that you would create creatively intuit your way through that, the way that you would brainstorm about things that matter, it's way easier to be creative when you have a fun space to play in, right? I think the pivotal politics space is a really nice space to play in as a non-specialist, just for thinking about these processes that when the sausage gets made. The idea of the pivotal politics model is that the proposer and the median voter have some opportunities for win-win. So if we flash this into utility imputation space, if we think about the disagreement point, what is that? So what's that disagreement point that allows us to think about the frame of reference for win-win? Well, the way that we've written this down, where P and M are both strictly greater than Q, then that means that the disagreement point utilities are Q minus P for the proposer and Q minus M for the median voter. Right? That's the negative absolute value of that. And what's going on here is there's a Pareto frontier of utility imputations that both parties prefer. There's a bargaining range that both parties prefer that are Pareto efficient and both parties prefer to the disagreement point. An interesting question is, how would you characterize the Pareto frontier in this model? And you can do that in the comfort of your own home. Just think that through for a second. What is the set of Pareto efficient outcomes? Regardless, we know that there exist win-win possibilities. How do we know that? Well, we know that the way that the game was written down, that setting things at exactly the median, that makes the median very happy, but it still benefits the proposer too. So that's a win-win. In fact, anything strictly to the right of Q is a win-win, so long as it isn't to the right of 2M minus Q. So long as we're moderate around the median ideal point, there's a lot of win-win possibilities here. Okay? So there's a bargaining range that emerges between the median voter and the proposer. And because the proposer moves first in a regular ultimatum game, all that happens is that we draw a horizontal line because they're going to get to eat all the benefits of the win-win. They draw that horizontal line, and next thing you know, we wind up exactly the utility imputation that we would get from 2M minus Q, from the furthest to the right, the most acceptable offer. So this bargaining problem is exactly like the ultimatum game. It's the same exact bargaining problem, but where the sources of bargaining power are very different than they were before. So long as we're living in between the median voters and the proposer's ideal point, so long as we're in that space in between them, things are zero-sum there, right? If we were to the left of the median voter, then moving to the right benefits them both. And if we were to the right of the proposer, then moving to the left benefits them both. But in between the median voter and the proposer, that's zero-sum land, and that's essentially where the whole model is taking place. And we're saying that because the proposer moves first, they get to eat all those benefits. Now, there might not be many benefits if the status quo is very close to the median voter's ideal point. Then the median voter has a lot of bargaining power, and the proposer only has so much wiggle room. But we've equipped the proposer with all that power. So the median voter here is decisive in the sense that they get to pick whether the thing wins or not. But they don't matter very much in the sense that the proposer might get to eat all the benefits. Whether or not they get to eat all the benefits depends on how good the status quo is. That's politics, right? So I think this pivotal politics model is a really great way to think about the start of political processes. For any given very important thing, there's a lot of sausage making, but just seeing it this way will really help you to have an orientation as you start to think through how to think through the sausage making. So what are we talking about today? Well, we had already talked about subgame perfection and backward induction, and most of the substantive lessons to teach about this sort of thing came from that week. I wanted to reserve this week to talk about how it plays out in these continuous spaces, in these sort of real line sort of worlds, where it's not just about a discrete choice, but about the setting of a level. The reason to do that is because there are some technical complications. You have to be flexible. You have to be ready to think about strategies as functions. But you're all ready for that. It's also because I think that the associated set of substantive lessons, though similar, are complementary to what we learned last week. So it's not just about credibility. It's not just about threats in the future. It's not just about looking down the tree. It's about how institutional setup influences that, how first movers or last movers influence that, how the rules in play, when appropriately encoded, shape the equilibrium predictions that we make in our fake mathematical worlds. And it's with that fakeness in mind that I'd like to conclude with a provocative thought. So the Ultimatum game has a very stark prediction, right? So with the 0-0 disagreement point, player one gets to keep the whole dollar. They're trying to figure out how to divide a dollar in a way that benefits them. And because of that weird wonky thing where there isn't a strictly greatest number, strictly less than one, the unique subgame-perfect equilibrium of the Ultimatum game is player one keeps the whole thing and player two accepts all offers, including the one that gets accepted. Now, I don't know about you, but that strikes me as a little bit nasty and gross. Now, in international relations, it doesn't bother me all that much because anarchy is what it is, and I know that the recourse of fighting is strong, and I hope to have faith in... Quiet! Quiet! Down. Down. Sit. Quiet. Down. Down. Stay. Good boy. Good boy. And so, no. Sit. Down. 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 Chewy. Chewy, down. No. Sit. Down. 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 Sit down. Down. Good boy. Stay. You know, among states, it's not that big of a deal, maybe, and we'd like to think the deterrence will hold, and the war is very costly, and the disagreement points of war are very bad. Such isn't always the case. And we'd like to think that, you know, that first mover advantage in the Ultimatum game in international relations isn't such a big deal because maybe I'm strong enough that I have enough bargaining power that I still get better deals. But if we're thinking about two citizens trying to figure out how to divide a dollar, chances are excellent that this perverse outcome that we get in the Ultimatum game may strike you as unfair on a normative level. It strikes many people as unfair on a normative level. It's okay, you can say that. It's fine. Many people don't like situations where one person has everything and the other has nothing. It's Pareto efficient, but it's highly unegalitarian. Go back to bargaining week. And you can imagine that the Ultimatum game, with this stark negative prediction that rubs people wrong on a normative way, you can imagine that that's something that you take to the lab. You want to see if that's what people actually do. And it turns out that most people don't try to keep everything. Maybe they say, okay, I'll keep 3/4 and you keep 1/4. Maybe I'll go 50-50, or maybe I'll keep 9/10 and I give you 1/10. It doesn't matter. They're all equally non-equilibrium. All right? So why do they do that? Well, maybe they have some egalitarian or altruistic instincts. Maybe that x1 minus x is actually the wrong utility function. The utility functions that we wrote down left no possibility for altruism or egalitarianism for the players. It just said that you want x to be high and I want x to be low. That's not the way that I feel as I go through life, though. I don't know about you, but I don't want to live in a world where I have everything and everybody else has nothing. And I don't think that you do either. Now, is this a rationality problem? No. It's not a rationality problem at all. It means that I wrote down a simple utility function that tried to tell you a story, x and 1 minus x, and that utility function might not capture all of the nuances about how people feel about how to divide dollars in this scarce and normatively laden world that we live in. But now we'd have to try to get to the nitty-gritty. We'd have to ask behavior and psychology scholars, hey, what's the right set of weights to put on this? How much do I weigh having goodies versus feeling guilty for having all the goodies? What's my ideal point in terms of how many goodies I would have? Right? That's what it is. Suppose, instead, that I didn't just want X to be high. Suppose that my very favorite was I have 95 cents and you have 5. That way I don't have to feel all the way guilty. You can go buy 5 cents worth of something. Right? But I still have a whole lot. That's just an ideal point. We're playing pivotal politics now. So when you go to the lab, when you see these egalitarian instincts, this is one way of saying not that I think rationality is stupid, which it may be and probably is, but more, it turns out the ultimatum game is a stylized version about what people do, not because of the rationality part, but rather because we don't quite know how individuals navigate the trade-offs of wanting to have more stuff versus not wanting to have too much of the stuff. And those interior preferences, the result of those cross-cutting effects, if there's anything that we've learned from the Divergent novels, it's that nobody is purely selfless and that nobody is purely selfish. We all have these cross-cutting parts of our psyches. And when I tell you a story like the Ultimatum game, it's not with any hope of trying to tap into all of that. Instead, it's saying, suppose that we were dealing with a sociopath that only wanted more stuff. Now it gets pretty interesting to think about how you would amend the model. That's why I've been trying to ask this question. I think these models are very amenable to saying, hey, how would you change the model? But in the lab, it's like 15, 20, 25%. So I won't take everything in the lab. When people play the Ultimatum game in the lab, they'll set X equals like 0.8 or something. They'll say, okay, I won't be all the way egalitarian. And I certainly won't be so altruistic to say X equals 0.2. But I'll keep 80% and that leaves you 20%. That means that I can sleep tonight. So there were two ways to say that the Ultimatum game could be amended to make it comport better with what people do in the lab. One is change the utility functions to better tap into this potentiality for interior egalitarian versus selfish instincts. And two would be rationality is stupid. And they've both been tried with lots of success. But it's something that I would like to ask you now, because you're now far enough in that you have some taste. You get to have opinions on some of these things. If we went to the lab with the stark prediction that in the Ultimatum game, somebody keeps 100%, and then we saw that that the people in the lab that had the first move set X equals 0.8 instead of X equals 1. Is your instinct that our notion of optimization, our notion of rationality is off? Or is your instinct that we just don't fully understand the preferences of the people in question, and conditional on asking them deeper questions about their preferences, we would be able to keep rationality as it sits relatively intact? It's a hard question, and there isn't a right answer. But I think that your answer to that question will begin to help you to prepare for the end of the class. Because, if this is going to have meant anything to you, which is a huge if, but if it is, then it will be because you will have had an opportunity to ruminate on difficult questions like that one that don't have a right answer. And your answers to questions like those are incredibly telling about what sort of answers you're going to find compelling out in the real world. What sort of explanations you're going to be prepared to offer out in the real world. Is it something that is about behavioral assumptions that one can make about people? Or is it about the unique idiosyncrasies about the preferences within any individual person? Is the problem with rationality writ large? Or is the problem with U sub I? Though I don't quite know player I's utility function as well as I would want to. Regardless, what we're talking about here is relatively sophisticated. Most people, when they talk about rationality, have either a 100% view on the subject or a 0% view on the subject. They either think it's stupid or they think it's great. And For you to have gotten something out of this class, I would consider a success if you think neither of those things is true. If you think rationality just kind of is. It's just something that we use sometimes. And I think that the Ultimatum game in particular lays bare the fact that we have to accept these mathematical objects that we use, warts and all, if we're going to try to make sense of things. And then the process becomes not about getting to some utopian scientific, we've characterized humanity well through some kind of social science, but rather we're trying to achieve deep personal understanding of things. And I hope that these tools have become something that you can view as somewhat personal, like a piece of art or literature. No matter what, we still have 5 weeks of fun fables to look through, and we're going to add some interesting and cool wrinkles, but I really hope that today was one that meant a lot to you, because bargaining is everywhere in politics, and it's a hard thing to think through over time. Thanks for watching.